There are various mathematical descriptions of the electromagnetic field that are used in the study of electromagnetism, one of the four fundamental interactions of nature. In this article, several approaches are discussed, although the equations are in terms of electric and magnetic fields, potentials, and charges with currents, generally speaking. Topic: Vector field approach. The most common description of the electromagnetic field uses two three-dimensional vector fields called the electric field and the magnetic field. These vector fields each have a value defined at every point of space and time and are thus often regarded as functions of the space and time coordinates. As such, they are often written as E x, y, z, t electric field and B x, y, z, t magnetic field. If only the electric field E is non-zero, and is constant in time, the field is said to be an electrostatic field. Similarly, if only the magnetic field B is non-zero and is constant in time, the field is said to be a magnetostatic field. However, if either the electric or magnetic field has a time dependence, then both fields must be considered together as a coupled electromagnetic field using Maxwell's equations. Maxwell's equations in the vector field approach. The behavior of electric and magnetic fields, whether in cases of electrostatics, magnetostatics, or electrodynamics, electromagnetic fields, is governed by Maxwell's equations, where ρ is the charge density, which can and often does depend on time and position, epsilon 0 is the electric constant, mu 0 is the magnetic constant, and J is the current per unit area, also a function of time and position. The equations take this form with the international system of quantities. When dealing with only nondispersive isotropic linear materials, Maxwell's equations are often modified to ignore bound charges by replacing the permeability and permittivity of free space with the permeability and permittivity of the linear material in question. For some materials that have more complex responses to electromagnetic fields, these properties can be represented by tensors, with time dependence related to the material's ability to respond to rapid field changes, dispersion optics, Green-Kubo relations, and possibly also field dependencies representing nonlinear and/or non-local material responses to large amplitude fields, nonlinear optics. Potential field approach. Many times in the use and calculation of electric and magnetic fields, the approach used first computes an associated potential, the electric potential phi (var phi) for the electric field, and the magnetic potential A for the magnetic field. The electric potential is a scalar field, while the magnetic potential is a vector field. This is why sometimes the electric potential is called the scalar potential and the magnetic potential is called the vector potential. These potentials can be used to find their associated fields as follows: E equals minus phi minus T. Display style Math E equals Math nabla var phi frac partial Math a partial T B equals times a. Display style Math B equals Math nabla times Math a. Topic: Maxwell's equations in potential formulation. These relations can be substituted into Maxwell's equations to express the latter in terms of the potentials. Faraday's law and Gauss's law for magnetism reduce to identities, e.g., in the case of Gauss's law for magnetism, 0 equals 0. The other two of Maxwell's equations turn out less simply. These equations taken together are as powerful and complete as Maxwell's equations. Moreover, the problem has been reduced somewhat, as the electric and magnetic fields together had 6 components to solve for. In the potential formulation, there are only 4 components, the electric potential and the 3 components of the vector potential. However, the equations are messier than Maxwell's equations using the electric and magnetic fields. Gauge freedom. These equations can be simplified by taking advantage of the fact that only the electric and magnetic fields are physically meaningful quantities that can be measured, the potentials are not. There is a freedom to constrain the form of the potentials provided that this does not affect the resultant electric and magnetic fields, called gauge freedom. Specifically for these equations, for any choice of a twice differentiable scalar function of position and time lambda, if phi a is a solution for a given system, then so is another potential phi a given by phi equals phi minus lambda t. Display style var phi equals var phi frac partial lambda partial t. A equals a plus lambda. Display style mathbf a equals mathbf a plus mathbf nabla lambda. This freedom can be used to simplify the potential formulation. Either of 2 such scalar functions is typically chosen, the Coulomb gauge and the Lorenz gauge. Coulomb gauge. The Coulomb gauge is chosen in such a way that a equals 0. Display style mathbf nabla cdot mathbf a equals 0, which corresponds to the case of magnetostatics. In terms of lambda, this means that it must satisfy the equation 2 lambda equals minus display style nabla caret 2 lambda equals mathbf nabla cdot mathbf a. This choice of function results in the following formulation of Maxwell's equations: 2 phi equals minus rho epsilon 0. Display style nabla caret 2 var phi equals frac rho var epsilon underscore 0. 2 a minus mu 0 epsilon 0. 2 a t 2 equals minus mu 0 j plus mu 0 epsilon 0 phi t. Display style nabla caret 2 math bf a mu underscore 0 var epsilon underscore 0 frac partial caret 2 math bf a partial t caret 2 equals mu underscore 0 math bf j plus mu underscore 0 var epsilon underscore 0 nabla left frac partial var phi partial t right. Several features about Maxwell's equations in the Coulomb gauge are as follows. Firstly, solving for the electric potential is very easy, as the equation is a version of Poisson's equation. Secondly, solving for the magnetic vector potential is particularly difficult. This is the big disadvantage of this gauge. The third thing to note, and something which is not immediately obvious, is that the electric potential changes instantly everywhere in response to a change in conditions in one locality. For instance, if a charge is moved in New York at 1 p.m. local time, then a hypothetical observer in Australia who could measure the electric potential directly would measure a change in the potential at 1 p.m. New York time. This seemingly violates causality in special relativity, i.e. the impossibility of information, signals, or anything traveling faster than the speed of light. The resolution to this apparent problem lies in the fact that, as previously stated, no observers can measure the potentials, they measure the electric and magnetic fields. So, the combination of phi and a, t used in determining the electric field restores the speed limit imposed by special relativity for the electric field, making all observable quantities consistent with relativity. Topic: Lorenz gauge condition. A gauge that is often used is the Lorenz gauge condition. In this, the scalar function lambda is chosen such that a equals minus mu 0 epsilon 0 phi t. Display style mathbf nabla cdot mathbf a equals mu underscore 0 var epsilon underscore 0 frac partial var phi partial t, meaning that lambda must satisfy the equation 2 lambda minus mu 0 epsilon 0 2 lambda t 2 equals minus a minus mu 0 epsilon 0 phi t. Display style nabla caret 2 lambda mu underscore 0 var epsilon underscore 0 frac partial caret 2 lambda partial t caret 2 equals math bf nabla cdot math bf a mu underscore 0 var epsilon underscore 0 frac partial var phi partial t. The Lorenz gauge results in the following form of Maxwell's equations: 2 phi minus mu 0 epsilon 0 2 phi t 2 equals white medium square 2 phi equals minus rho epsilon 0. Display style nabla caret 2 var phi mu underscore 0 var epsilon underscore 0 frac partial caret 2 var phi partial t caret 2 equals box caret 2 var phi equals frac rho var epsilon underscore 0 2 a minus mu 0 epsilon 0 2 t 2 equals white medium square 2 a equals minus mu 0 j. Display style nabla caret 2 math bf a mu underscore 0 var epsilon underscore 0 frac partial caret 2 math bf a partial t caret 2 equals box caret 2 math bf a equals mu underscore 0 math bf j. The operator white medium square 2 display style box caret 2 is called the D'Alembertian. Some authors denote this by only the square white medium square display style box. These equations are inhomogeneous versions of the wave equation, with the terms on the right side of the equation serving as the source functions for the wave. As with any wave equation, these equations lead to two types of solution: advanced potentials, which are related to the configuration of the sources at future points in time, and retarded potentials, which are related to the past configurations of the sources. The former are usually disregarded where the field is to analyzed from a causality perspective. As pointed out above, the Lorenz gauge is no more valid than any other gauge since the potentials cannot be measured. Despite this, there are certain quantum mechanical phenomena in which potentials appear to affect particles in regions where the observable field vanishes throughout the region, for example as in the Aharonov-Bohm effect. However, these phenomena do not provide a means to directly measure the potentials nor to detect a difference between different but mutually gauge-equivalent potentials. The Lorenz gauge has the further advantage of the equations being Lorentz invariant. Topic: Extension to quantum electrodynamics. Canonical quantization of the electromagnetic fields proceeds by elevating the scalar and vector potentials phi x, a x from fields to field operators. Substituting 1 C2 equals epsilon 0 mu 0 into the previous Lorenz gauge equations gives 2 a minus 1 C 2 2 a T 2 equals minus mu 0 J display style nabla caret 2 math BF a frac 1 C caret 2 frac partial caret 2 math BF a partial T caret 2 equals mu underscore 0 math BF J 2 phi minus 1 C 2 2 phi T 2 equals minus rho epsilon 0 display style nabla caret 2 var phi frac 1 C caret 2 frac partial caret 2 var phi partial T caret 2 equals frac rho var epsilon underscore 0. Here J and rho are the current and charge density of the matter field. If the matter field is taken so as to describe the interaction of electromagnetic fields with the Dirac electron given by the four-component Dirac-Spinor field psi, the current and charge densities have form J equals minus E psi alpha psi rho equals minus E psi psi display style math J equals E psi caret dagger bold symbol alpha psi quad rho equals E psi caret dagger psi, where alpha are the first three Dirac matrices. Using this, we can rewrite Maxwell's equations as, which is the form used in quantum electrodynamics. Topic: Geometric algebra formulations. Analogous to the tensor formulation, two objects, one for the field and one for the current, are introduced. In geometric algebra (GAR), these are multivectors. The field multivector, known as the Riemann-Silberstein vector, is F equals E plus I C B equals E K sigma K plus I C B K sigma K. Display style Math F equals Math E plus IC Math B equals E caret K sigma underscore K plus ICB caret K sigma underscore K, and the current multivector is C rho minus J equals C rho minus J K sigma K Display style C rho math BF J equals C rho J caret K sigma underscore K, where in the algebra of physical space APS C 3 0 R display style C L underscore 3 0 math B R with the vector basis sigma K display style sigma underscore K. The unit pseudoscalar is I equals sigma 1 sigma 2 sigma 3 display style I equals sigma underscore 1 sigma underscore 2 sigma underscore 3, assuming an orthonormal basis. Orthonormal basis vectors share the algebra of the Pauli matrices, but are usually not equated with them. After defining the derivative equals sigma K display style bold symbol nabla equals sigma caret K partial underscore K, Maxwell's equations are reduced to the single equation. In 3 dimensions, the derivative has a special structure allowing the introduction of a cross product F equals F plus F equals F plus I times F display style bold symbol nabla math BF F equals bold symbol nabla CDOT math BF F plus bold symbol nabla wedge math BF F equals bold symbol nabla CDOT math BF F plus I bold symbol nabla times math BF F, from which it is easily seen that Gauss's law is the scalar part, the Ampere-Maxwell law is the vector part, Faraday's law is the pseudovector part, and Gauss's law for magnetism is the pseudoscalar part of the equation. After expanding and rearranging, this can be written as E minus rho E0 minus C times B minus mu 0 E0 E T minus mu 0 J plus I times E plus B T plus I C B equals 0. Display style left bold symbol nabla CDOT math BF E frac rho epsilon underscore 0 right C left bold symbol nabla times math BF B mu underscore 0 epsilon underscore 0 frac partial math BF E partial T mu underscore 0 math BF J right plus I left bold symbol nabla times math BF E plus frac partial math BF B partial T right plus IC left bold symbol nabla CDOT math BF B right equals 0. We can identify APS as a subalgebra of the spacetime algebra star C 1 3 R display style C L underscore 1 3 math B R, defining sigma K equals gamma K gamma 0 display style sigma underscore K equals gamma underscore K gamma underscore 0 and I equals gamma 0 gamma 1 gamma 2 gamma 3 Display style I equals gamma underscore 0 gamma underscore 1 gamma underscore 2 gamma underscore 3. The gamma mu display style gamma underscore mu s have the same algebraic properties of the gamma matrices, but their matrix representation is not needed. The derivative is now equals gamma mu display style nabla equals gamma caret mu partial underscore mu. The Riemann-Silberstein becomes a bivector f equals e plus I c b equals e 1 gamma 1 gamma 0 plus e 2 gamma 2 gamma 0 plus e 3 gamma 3 gamma 0 minus c b 1 gamma 2 gamma 3 plus b 2 gamma 3 gamma 1 plus b 3 gamma 1 gamma 2. Display style f equals math BF e plus IC math BF b equals e caret 1 gamma underscore 1 gamma underscore 0 plus e caret 2 gamma underscore 2 gamma underscore 0 plus e caret 3 gamma underscore 3 gamma underscore 0 c b caret 1 gamma underscore 2 gamma underscore 3 plus b caret 2 gamma underscore 3 gamma underscore 1 plus b caret 3 gamma underscore 1 gamma underscore 2, and the charge and current density become a vector J equals J mu gamma mu equals c rho gamma 0 plus j k gamma k equals gamma 0 c rho minus j k sigma k. Display style j equals j caret mu gamma underscore mu equals c rho gamma underscore 0 plus j caret k gamma underscore k equals gamma underscore 0 c rho j caret k sigma underscore k. Owing to the identity gamma 0 equals gamma 0 gamma 0 0 plus gamma 0 gamma k k equals 0 plus sigma k k equals 1 c t plus. Display style gamma underscore 0 nabla equals gamma underscore 0 gamma caret 0 partial underscore 0 plus gamma underscore 0 gamma caret k partial underscore k equals partial underscore 0 plus sigma caret k partial underscore k equals frac 1 c dfrac partial t plus bold symbol nabla. Maxwell's equations reduced to the single equation. Topic: Differential forms approach. Topic: Field 2 form. In free space, where epsilon topic epsilon 0 and mu 0 are constant everywhere. Maxwell's equations simplify considerably once the language of differential geometry and differential forms is used. In what follows, CGS Gaussian units, not SI units are used. To convert to SI, see here, the electric and magnetic fields are now jointly described by a two-form F in a four-dimensional spacetime manifold. The Faraday tensor F mu display style F underscore mu electromagnetic tensor can be written as a two-form in Minkowski space with metric signature as F 1 2 F mu d x mu d x nu equals b x d y d z plus b y d z d x plus b z d x d y plus e x dx dt plus ey dy dt plus ez dz dt display style begin aligned math BF f equivalent and frac 1 2 F underscore mu mathrm d x caret mu wedge mathrm d x caret nu equals and b underscore x mathrm d y wedge mathrm d z plus b underscore y mathrm d z wedge mathrm d x plus b underscore z mathrm d x wedge mathrm d y plus the underscore x mathrm d x wedge mathrm d t plus the underscore y mathrm d y wedge mathrm d t plus the underscore z mathrm d z wedge mathrm d t end aligned, which, as the curvature form, is the exterior derivative of the electromagnetic four potential F equals dA equals mu a nu dx mu dx nu display style math BF F equals mathrm d math BF a equals partial underscore mu a underscore nu mathrm d x caret mu wedge mathrm d x caret nu. The source-free equations can be written by the action of the exterior derivative on this two-form. But for the equations with source terms, Gauss's law and the Ampere-Maxwell equation, the Hodge dual of this two-form is needed. The Hodge star dual takes a p-form to a n-p form, where n is the number of dimensions. Here, it takes the two-form F and gives another two-form in 4 dimensions, n-p. Topic 4-2 2. For the basis cotangent vectors, the Hodge dual is given as see here d x d y equals minus d z d t d x d t equals d y d z display style star mathrm d x wedge mathrm d y equals mathrm d z wedge mathrm d t quad star mathrm d x wedge mathrm d t equals mathrm d y wedge mathrm d z and so on. Using these relations, the dual of the Faraday two-form is the Maxwell tensor F equals minus b x d x d T minus B Y D Y D T minus B Z D Z D T plus E X D Y D Z plus E Y D Z D X plus E Z D X D Y. Display style star math BF F equals B underscore X mathrm D X wedge mathrm D TB underscore Y mathrm D Y wedge mathrm D TB underscore Z mathrm D Z wedge mathrm D T plus E underscore X mathrm D Y wedge mathrm D Z plus E underscore Y mathrm D Z wedge mathrm D X plus E underscore Z mathrm D X wedge mathrm D Y. Topic: Current 3 form, dual current 1 form. Here, the 3 form J is called the electric current form or current 3 form. J equals rho D X D Y D Z minus J X D T D Y D Z minus J Y D T D Z D X minus J Z D T D X D Y. Display style math J equals rho mathrm D X wedge mathrm D Y wedge mathrm D Z J underscore X mathrm D T wedge mathrm D Y wedge mathrm D Z J underscore Y mathrm D T wedge mathrm D Z wedge mathrm D X J underscore Z mathrm D T wedge mathrm D X wedge mathrm D Y. With the corresponding dual 1 form J equals minus rho D T plus J X D X plus J Y D Y plus J Z D Z. Display style star math J equals rho mathrm D T plus J underscore X mathrm D X plus J underscore Y mathrm D Y plus J underscore Z mathrm D Z. Maxwell's equations then reduce to the Bianchi identity and the source equation, respectively, where D denotes the exterior derivative, a natural coordinate and metric-independent differential operator acting on forms, and the dual Hodge star operator. Display style star is a linear transformation from the space of 2 forms to the space of 4-2 forms defined by the metric in Minkowski space in 4 dimensions, even by any metric conformal to this metric. The fields are in natural units where 1/4 P0 equals 1. Since D2 equals 0, the 3 form J satisfies the conservation of current continuity equation D J equals D 2 F equals 0. display style mathrm d math BF J equals mathrm d caret 2 star math BF F equals 0. The current 3 form can be integrated over a 3-dimensional spacetime region. The physical interpretation of this integral is the charge in that region if it is spacelike, or the amount of charge that flows through a surface in a certain amount of time if that region is a spacelike surface cross a timelike interval. As the exterior derivative is defined on any manifold, the differential form version of the Bianchi identity makes sense for any 4-dimensional manifold, whereas the source equation is defined if the manifold is oriented and has a Lorenz metric. In particular, the differential form version of the Maxwell equations are a convenient and intuitive formulation of the Maxwell equations in general relativity. Note, in much of the literature, the notations J displaystyle math BF J and J displaystyle star math BF J are switched so that J displaystyle math BF J is a one form called the current and J displaystyle star math BF J is a 3 form called the dual current. Topic: Linear macroscopic influence of matter. In a linear, macroscopic theory, the influence of matter on the electromagnetic field is described through more general linear transformation in the space of 2 forms. We call C lambda 2 F G element of lambda 4 minus 2 display style C lambda caret 2 ni math BF F mapsto math BF G in lambda caret 4 to 2. The constitutive transformation. The role of this transformation is comparable to the Hodge duality transformation. The Maxwell equations in the presence of matter then become d F equals 0 display style mathrm d math BF F equals 0 d G equals J display style mathrm d math BF G equals math BF J, where the current 3 form J still satisfies the continuity equation dJ equals 0. When the fields are expressed as linear combinations of exterior products of basis forms theta p F equals 1 2 F p Q theta p theta Q display style math BF F equals frac 1 2 F underscore PQ math BF theta caret P wedge math BF theta caret Q. The constitutive relation takes the form G P Q equals C P Q M N F M N display style G underscore PQ equals C underscore PQ caret Minnesota F underscore Minnesota, where the field coefficient functions are antisymmetric in the indices and the constitutive coefficients are antisymmetric in the corresponding pairs. In particular, the Hodge duality transformation leading to the vacuum equations discussed above are obtained by taking C P Q M N equals 1 2 G M A G N B E A B P Q minus G Display style C underscore PQ caret Minnesota equals frac 1 2 G caret mar G caret NB epsilon underscore ABPQ SQRT G, which up to scaling is the only invariant tensor of this type that can be defined with the metric. In this formulation, electromagnetism generalizes immediately to any four-dimensional oriented manifold or with small adaptations any manifold. Topic: Alternate metric signature. In the particle physicist's sign convention for the metric signature plus minus minus minus, the potential one form is A equals phi d t minus A x d x minus A y d y minus A z d z. Display style mathbf a equals phi mathrm d ta underscore x mathrm d x a underscore y mathrm d y a underscore z mathrm d z. The Faraday curvature 2 form becomes f 1 2 f mu nu d x mu d x nu equals e x d t d x plus e y d t d y plus e z d t d z minus b x d y d z minus BYDZ dx minus BZ dx dy. Display style begin aligned math BF f equivalent and frac 1 2 f underscore mu nu mathrm d x caret mu wedge mathrm d x caret nu equals and e underscore x mathrm d t wedge mathrm d x plus e underscore y mathrm d t wedge mathrm d y plus e underscore z mathrm d t wedge mathrm d zb underscore x mathrm d y wedge mathrm d zb underscore y mathrm d z wedge mathrm d xb underscore z mathrm d x wedge mathrm d y end aligned, and the Maxwell tensor becomes f equals minus ex dy dz minus ey dz dx minus ez dx d y minus b x d t d x minus b y d t d y minus b z d t d z. Display style star math BF f equals e underscore x mathrm d y wedge mathrm d z e underscore y mathrm d z wedge mathrm d x e underscore z mathrm d x wedge mathrm d y b underscore x mathrm d t wedge mathrm d x b underscore y mathrm d t wedge mathrm d y b underscore z mathrm d t wedge mathrm d z. The current 3 form J is J equals minus rho d x d y d Z plus J X D T D Y D Z plus J Y D T D Z D X plus J Z D T D X D Y. Display style Math J equals rho mathrm D X wedge mathrm D Y wedge mathrm D Z plus J underscore X mathrm D T wedge mathrm D Y wedge mathrm D Z plus J underscore Y mathrm D T wedge mathrm D Z wedge mathrm D X plus J underscore Z mathrm D T wedge mathrm D X wedge mathrm D Y. And the corresponding dual one form is J equals minus rho D T plus J X D X plus J Y D Y plus J Z D Z. Display style star Math J equals rho mathrm D T plus J underscore X mathrm D X plus J underscore Y mathrm D Y plus J underscore Z mathrm D Z. The current norm is now positive and equals J equals rho 2 plus J X 2 plus J Y 2 plus J Z 2 1. Display style Math J wedge star Math J equals rho caret 2 plus J underscore X caret 2 plus J underscore Y caret 2 plus J underscore Z caret 2 star 1. With the canonical volume form 1 equals D T D X D Y D Z. Display style asterisk 1 equals mathrm D T wedge mathrm D X wedge mathrm D Y wedge mathrm D Z. Topic: Curved spacetime. Topic: Traditional formulation. Matter and energy generate curvature of spacetime. This is the subject of general relativity. Curvature of spacetime affects electrodynamics. An electromagnetic field having energy and momentum also generates curvature in spacetime. Maxwell's equations in curved spacetime can be obtained by replacing the derivatives in the equations in flat spacetime with covariant derivatives. Whether this is the appropriate generalization requires separate investigation. The sourced and source-free equations become CGS Gaussian units for pi c j beta equals alpha f alpha beta plus gamma alpha mu alpha f mu beta plus gamma beta mu alpha f alpha mu equals d e f alpha f alpha beta equals d e f f alpha beta alpha display style 4 pi over c j caret beta equals partial underscore alpha f caret alpha beta plus gamma caret alpha underscore mu alpha f caret mu beta plus gamma caret beta underscore mu alpha f caret alpha mu stackrel mathrm def equals nabla underscore alpha f caret alpha beta stackrel mathrm def equals f caret alpha beta underscore alpha and 0 equals gamma f alpha beta plus beta f gamma alpha plus alpha f beta gamma equals gamma f alpha beta plus beta f gamma alpha plus alpha f beta gamma display style 0 equals partial underscore gamma f underscore alpha beta plus partial underscore beta f underscore gamma alpha plus partial underscore alpha f underscore beta gamma equals nabla underscore gamma f underscore alpha beta plus nabla underscore beta f underscore gamma alpha plus nabla underscore alpha f underscore beta gamma. Here gamma alpha mu beta display style gamma caret alpha underscore mu beta is a Christoffel symbol that characterizes the curvature of spacetime, and alpha is the covariant derivative. Topic: Formulation in terms of differential forms. The formulation of the Maxwell equations in terms of differential forms can be used without change in general relativity. The equivalence of the more traditional general relativistic formulation using the covariant derivative with the differential form formulation can be seen as follows. Choose local coordinates x alpha, which gives a basis of 1 forms dx alpha in every point of the open set where the coordinates are defined. Using this basis and CGS Gaussian units, we define the antisymmetric field tensor f ab, corresponding to the field 2 form f equals 1 2 f alpha beta d x alpha d x beta. Display style math f equals frac 1 2 f underscore alpha beta mathrm d x caret alpha wedge mathrm d x caret beta. The current vector infinitesimal 3 form j equals 4 pi c 1 6 j alpha minus g e alpha beta gamma delta d x beta d x gamma d x delta. Display style Math J equals 4 pi over C left frac 1 6 J caret alpha sqrt G epsilon underscore alpha beta gamma delta mathrm D x caret beta wedge mathrm D x caret gamma wedge mathrm D x caret delta right. The epsilon tensor contracted with the differential 3 form produces 6 times the number of terms required. Here G is as usual the determinant of the matrix representing the metric tensor, G-ab. A small computation that uses the symmetry of the Christoffel symbols, i.e. the torsion freeness of the Levi-Civita connection and the covariant constantness of the Hodge star operator then shows that in this coordinate neighborhood we have the Bianchi identity D F equals 2 gamma F alpha beta plus beta F gamma alpha plus alpha F beta gamma D x alpha D x beta D x gamma equals 0. Display style mathrm D math F equals 2 partial underscore gamma F underscore alpha beta plus partial underscore beta F underscore gamma alpha plus partial underscore alpha F underscore beta gamma mathrm D x caret alpha wedge mathrm D x caret beta wedge mathrm D x caret gamma equals 0. The source equation D F equals 1 6 F alpha beta alpha minus G E beta gamma delta eta D x gamma D x delta D x eta equals J. Display style mathrm D star math F equals frac 1 6 F caret alpha beta underscore alpha sqrt G epsilon underscore beta gamma delta eta mathrm D x caret gamma wedge mathrm D x caret delta wedge mathrm D x caret eta equals math J. The continuity equation D J equals 4 pi C J alpha alpha minus G E alpha beta gamma delta D x alpha D x beta D x gamma D x delta equals 0. Display style mathrm D math J equals 4 pi over C J caret alpha underscore alpha sqrt G epsilon underscore alpha beta gamma delta mathrm D x caret alpha wedge mathrm D x caret beta wedge mathrm D x caret gamma wedge mathrm D x caret delta equals 0. Topic: Classical electrodynamics as the curvature of a line bundle. An elegant and intuitive way to formulate Maxwell's equations is to use complex line bundles or a principal U bundle, on the fibers of which U acts regularly. The principal U connection on the line bundle has a curvature F. Topic 2, which is a 2 form that automatically satisfies df 0 and can be interpreted as a field strength. If the line bundle is trivial with flat reference connection D, we can write topic D plus A and F DA with A, the one form composed of the electric potential and the magnetic vector potential. In quantum mechanics, the connection itself is used to define the dynamics of the system. This formulation allows a natural description of the Aharonov-Bohm effect. In this experiment, a static magnetic field runs through a long magnetic wire, e.g., an iron wire magnetized longitudinally. Outside of this wire, the magnetic induction is zero, in contrast to the vector potential, which essentially depends on the magnetic flux through the cross-section of the wire and does not vanish outside. Since there is no electric field either, the Maxwell tensor F equals 0 throughout the spacetime region outside the tube, during the experiment. This means by definition that the connection is flat there. However, as mentioned, the connection depends on the magnetic field through the tube, since the holonomy along a non-contractible curve encircling the tube is the magnetic flux through the tube in the proper units. This can be detected quantum mechanically with a double-slit electron diffraction experiment on an electron wave traveling around the tube. The holonomy corresponds to an extra phase shift, which leads to a shift in the diffraction pattern. Topic: Discussion. Following are the reasons for using each of such formulations. Topic: Potential formulation. In advanced classical mechanics it is often useful, and in quantum mechanics frequently essential, to express Maxwell's equations in a potential formulation involving the electric potential, also called scalar potential phi, and the magnetic potential, also called vector potential A. For example, the analysis of radio antennas makes full use of Maxwell's vector and scalar potentials to separate the variables, a common technique used in formulating the solutions of differential equations. The potentials can be introduced by using the Poincaré lemma on the homogeneous equations to solve them in a universal way. This assumes that we consider a topologically simple, e.g. contractible space. The potentials are defined as in the table above. Alternatively, these equations define E and B in terms of the electric and magnetic potentials, which then satisfy the homogeneous equations for E and B as identities. Substitution gives the non-homogeneous Maxwell equations in potential form. Many different choices of A and phi are consistent with given observable electric and magnetic fields E and B, so the potentials seem to contain more, classically unobservable information. The non-uniqueness of the potentials is well understood, however. For every scalar function of position and time lambda x, t, the potentials can be changed by a gauge transformation as phi equals phi minus lambda t a equals a plus lambda. Display style var phi equals var phi frac partial lambda partial t quad math bf a equals math bf a plus math bf nabla lambda, without changing the electric and magnetic field. Two pairs of gauge transformed potentials phi a and phi a are called gauge equivalent, and the freedom to select any pair of potentials in its gauge equivalence class is called gauge freedom. Again, by the Poincaré lemma and under its assumptions, gauge freedom is the only source of indeterminacy, so the field formulation is equivalent to the potential formulation if we consider the potential equations as equations for gauge equivalence classes. The potential equations can be simplified using a procedure called gauge fixing. Since the potentials are only defined up to gauge equivalence, we are free to impose additional equations on the potentials, as long as for every pair of potentials there is a gauge equivalent pair that satisfies the additional equations, i.e. if the gauge fixing equations define a slice to the gauge action. The gauge-fixed potentials still have a gauge freedom under all gauge transformations that leave the gauge-fixing equations invariant. Inspection of the potential equations suggests two natural choices. In the Coulomb gauge, we impose A equals 0, which is mostly used in the case of magnetostatics when we can neglect the C-22A, T2 term. In the Lorenz gauge, named after the Dane Ludwig Lorenz, we impose a plus 1 C 2 phi T equals 0. Display style mathbf nabla cdot mathbf a plus frac 1 c caret 2 frac partial var phi partial t equals 0. The Lorenz gauge condition has the advantage of being Lorentz invariant and leading to Lorentz invariant equations for the potentials. Topic: Manifestly covariant tensor approach. Maxwell's equations are exactly consistent with special relativity, i.e., if they are valid in one inertial reference frame, then they are automatically valid in every other inertial reference frame. In fact, Maxwell's equations were crucial in the historical development of special relativity. However, in the usual formulation of Maxwell's equations, their consistency with special relativity is not obvious, it can only be proven by a laborious calculation. For example, consider a conductor moving in the field of a magnet. In the frame of the magnet, that conductor experiences a magnetic force. But in the frame of a conductor moving relative to the magnet, the conductor experiences a force due to an electric field. The motion is exactly consistent in these two different reference frames, but it mathematically arises in quite different ways. For this reason and others, it is often useful to rewrite Maxwell's equations in a way that is manifestly covariant, i.e. obviously consistent with special relativity, even with just a glance at the equations, using covariant and contravariant 4-vectors and tensors. This can be done using the M-tensor F, or the 4-potential A, with the 4-current J. See covariant formulation of classical electromagnetism. Topic: Differential forms approach. Gauss's law for magnetism and the Faraday-Maxwell law can be grouped together since the equations are homogeneous, and be seen as geometric identities expressing the field F A2 form, which can be derived from the 4-potential A. Gauss's law for electricity and the Ampère-Maxwell law could be seen as the dynamical equations of motion of the fields, obtained via the Lagrangian principle of least action, from the interaction term AJ introduced through gauge covariant derivatives, coupling the field to matter. For the field formulation of Maxwell's equations in terms of a principle of extremal action, see electromagnetic tensor. Often, the time derivative in the Faraday-Maxwell equation motivates calling this equation dynamical, which is somewhat misleading in the sense of the preceding analysis. This is rather an artifact of breaking relativistic covariance by choosing a preferred time direction. To have physical degrees of freedom propagated by these field equations, one must include a kinetic term FF for A, and take into account the non-physical degrees of freedom that can be removed by gauge transformation AA-d alpha. See also gauge fixing and Faddeev-Popov ghosts. Topic: Geometric calculus approach. This formulation uses the algebra that spacetime generates through the introduction of a distributive, associative but not commutative product called the geometric product. Elements and operations of the algebra can generally be associated with geometric meaning. The members of the algebra may be decomposed by grade, as in the formalism of differential forms, and the geometric product of a vector with a k vector decomposes into a k-1 vector and a k+1 vector. the k-1 vector component can be identified with the inner product and the k+1 vector component with the outer product. It is of algebraic convenience that the geometric product is invertible, while the inner and outer products are not. The derivatives that appear in Maxwell's equations of vectors and electromagnetic fields are represented by the Faraday bivector F. This formulation is as general as that of differential forms for manifolds with a metric tensor, as then these are naturally identified with R forms and there are corresponding operations. Maxwell's equations reduce to one equation in this formalism. This equation can be separated into parts as is done above for comparative reasons. See also: Ricci calculus, electromagnetic wave equation, speed of light, electric constant, magnetic constant, free space, near and far field, electromagnetic field, electromagnetic radiation, quantum electrodynamics. Notes